Okay, I'm going to start by taking a look at part one of the two. I'm going to break it up in two parts, sections one and section two of chapter four. Okay, energy analysis of a closed system. All right, here's some of the main topics that I'm going to go through. We're going to first start with moving boundary work. Um, you know, you can think of that in terms of, at least when we look at the problems, uh, like a piston cylinder combination where the piston's moving up and down, so we're changing the volume, and we're doing work to move that. The next one we look at demonstrate first law of thermodynamics, energy balance for a closed system. Closed system basically is no energy being exchanged with the environment. Um, look at specific heat and at constant volume. Specific heat being, amount of heat to raise some quantity of mass, or some unit of mass, I should say, um, a degree C, right? And then next, specific heat calculations of changes in internal energy and enthalpy. And enthalpy is just going to be defined basically as internal energy plus the pressure times volume. Incompressible substances and changes in their internal energy and enthalpy. And then we'll look at solving energy balance problems for closed systems. Okay. So first part, moving boundary work. Okay. And we take a look at it from the perspective, what's happening here, as heat, or, heat is added onto the system typically. And we can think about that in terms of work, right? Well, we start off with our same basic equation. And, if you think about this as like some incremental part of work is equal to whatever the force is times that incremental distance, okay? Um, so in terms of R, we can say, define this basically, it's pressure times area, right? Because pressure is defined as force per unit area times that little incremental distance. So a nice way to look at it is here. So visually, this is kind of what's happening, right? We have delta S, either, you know, positive or negative if it's decreasing or increasing here. Okay. So if we wanted to find the total work done, we would have to think about it in terms of like from, whatever position one, maybe it's like you're right here and then you go up to position two. So you'd find the integral of this. Okay. And we'll take a look at that, like graphically, what that means. Okay. And just talking about this quasi-equilibrium process, um, how do we define it? We're going to find that if we expand, we do work. If it's positive for expansion, and the work is going to turn out to be negative for compression. Okay. All right. So if we look at that graphically, kind of what's happening, we're starting off with pressure. So we have some process going on here. And what we're going to do is we're actually going to get the area under this curve, right? Or whichever curve, depending upon the process or the path that it follows, right? And one of the things that you can recognize here is that depending upon its path, right, whatever path this is following, um, it'll do different amounts of work because, of course, the area underneath it will be different, right? And here's kind of the way to look at it, sort of visually, what's happening here. So what are we doing when we're talking about like this little incremental piece of work that's done? It's basically going to be this little delta A, right? So if we go back, um, sorry, yeah, the little delta A is this P dV, right here. Okay. So if we sum all of those together, those little incremental areas, put all of them together, then we can come up with like the total work, going from point, whatever position one is to position two. Okay. And that's it. So, so really it's just this, right? It's the area under that curve, right? And the last point is just that. That just summarizes it. Okay. And we can think about it in terms of this, like this is going back and forth essentially between the two states, right? When the piston's moving in and out. Maybe this is an engine, a gas engine or something, or a steam engine. And what we're going to end up having is that, like, going in one direction in the process, you have a certain amount of work done, and then being done to move this, and then the difference between the two essentially is this area here, right? So this is like work going in one direction, and this is work coming back in the other direction. Okay, going from like point 1 to 2, here goes back 2 to 1, and it's just cycling between these. Okay. So let's think about this in terms of like an example here. We can look at an example where we add heat. Let's say you have water in here and you add heat to it, um, and what work is going to be done here, right? Okay, so we just start off with our you know our equation for work, boundary work being done, and if we look at it in terms of, one of the things we find here is we have, like, there's a constant pressure here, um, and so we can pull out pressure, just put it on the left hand side of um, the integration symbol. And then, since it's a constant pressure in this case, so this is constant pressure process, um, then it just becomes, if you did the integral of this, it's just going to be V2 minus V1 volume. Okay. Now we can also write this in terms of the specific volumes. So, this is, which is just, volume per mass. So then we can pull out mass over here. Then we know these are, you know, volume per mass, volume per mass. Okay. And we can look at the process diagram. And basically, if you look at it, it's going to be a straight line because the pressure is constant as you go between these two volumes. And then you could figure out the work. The work is just, of course, just what's underneath this. Okay. So like going from 1 to 2, where the volume is increasing, or in this case, they show it as specific volume. It's just this area. So it's just whatever distance from here to here times the pressure. Okay. And that's all this is really showing. Okay, so now here's the case for a constant volume process, right? So in this case, we have the pressures changing, and it's giving off heat to its environment. Um, pressures pressure's changing, but in this case, the volume stays the same. Okay, and we have a change in temperature here. Okay, and with a diagram, we can show it to be just, here's a change in volume, of course, but the volume in this case stays the same. All right, or specific volume if you want. This is in terms of volume, PV. So boundary work for an isothermal compression process. So in this case, we have a constant temperature, and we can write the equation just as before. And one of the substitutions that we can make for this is setting the mass times the ideal gas constant times that initial the temperature, the constant temperature, and that equal to C. Let me just rewrite it like this: the pressure equal to C over V. So then when we do that, we replace the P with a C, and this is just C over V. And when we do the integration of that, it just becomes the natural log of the V2 over V1. Okay. All right. So like here, and this is an example doing boundary work. So we make the substitution, and then it just becomes dV over V. This is what you integral. This is the constant, and then it's just by definition, for this type of an integral, 1 over V dV is essentially just the natural log of when you do it between these two limits, just becomes the natural log of V2 over V1. Okay, so this would be the standard form you would see in calculus, or integral calculus. And then we have here's our initial one, and then the natural log of, if we make that substitution back in for C, P1 to V1, it's just going to be the natural or V2 or V1. Okay. And that essentially is just, the area underneath this curve, right? Okay. And the last one is the boundary work for a polytropic process. So polytropic process basically follows this relationship where you have pressure times volume times raised to some power of n throughout the process. You have that's equal to a constant. Okay, so we could just rewrite this. Divide both sides by v raised to the n power, and we're looking at boundary work as before. Here's our standard equation. We make this substitution in here for pressure, and then we go through and we perform the integration, and the end result is just here's our equation after we perform the integration between those two limits, and here's our equation. And the last part of this, what we can do is we can make a substitution in here for with mass times the for our pressure volume, mass times the ideal gas constant times the difference between these two temperatures. Okay, and here it is, sort of graphically, and here's the process. So the area is going to be between, of course, between these two. The area underneath this curve between V1 and V2. Okay, and we'll take a look at some of these examples. The textbook has examples also worked out. And then just taking a look at what it looks like if we have expansion of a gas against a spring. Okay, so in this case, you're going to have essentially a linear line, and you just make the assumption that this is a linear spring, of course, in the range that we care about, and in terms of its range of compression or extension. And so heat is added to here, and what happens? The volume expands, pushing up on the spring. And if we just do the, determine the work here, we have just the areas under these curves. Okay, and that's pretty much it. But we'll take a look at some examples also of each of these. Okay, I'm going to look at energy balance for closed systems. Okay. All right, so here's our equation, essentially saying whatever, the difference in energy coming in minus the energy going out is just equal to the change in internal energy. Okay. We can also do this in terms of a rate, saying this is like, this is energy typically used for the SI system, use joules, and this could be like joules per second or watts, right? If we're talking SI system. The rate at which also the change in rate the change in rate between the rate which it comes in minus the rate at which it's leaving, energy is leaving, is just the rate at which the energy is changing within the system. Okay. So what's the relationship between them? It's just, in this case, heat. If we want to talk about heat, Q is typically used for heat. The rate at which heat's coming in or leaving a system times delta T gives you the actual heat, right? So it's just the rate, and this is assuming that's constant rate, times delta T gives you the total heat. Okay, and work is also the same thing, right? And we can also represent, it's really just kind of going back and forth between these equations. The change in internal energy is just the rate at which it changes times the delta T, okay, assuming that this is a constant. All right, and then we can think about it in terms of energy balance per unit mass. So we can also write this equation in terms of unit mass, okay, because this is a closed system. We're not exchanging mass with the environment, okay. And like you could write this way, the same kind of thing in terms of, if you're thinking about it, incremental changes, all right? And the same thing here, in incremental changes in per unit mass, energy per unit mass. Okay, then of course Um, if we have a cycle, essentially, whatever work is done is going to be the net of the change in heat in the system, right? Because it's a closed system. And then also the rate's the same thing. Okay, so net out is just equal to whatever energy is brought in. Okay, if it's a cycle. Okay, right. And the reason for that is like if you think about it, if you put this on the other side of the equation, essentially it becomes net out minus heat in equals zero, essentially. Okay. All right. So we could show that like here, just in general. Here's a cycle. You're just going around doing the same thing over and over again. You can think about it in terms of like a piston moving up and down, driving some kind of engine. Okay. So if we talk about it in terms of like the total change in the energy of the system, um, so if we're talking about like, from closed systems, we say whatever's in minus whatever's out. This gives you the change in the system, right? And then the same thing here, net in minus the difference between these two, and here's the difference between these two for work. Okay. What I had said previously, this is for a cycle, right? This is the general form. Okay. So here's the general form. And then we can say for a stationary system. So if, the system's not moving, it's just changing internal energy here. If we do it in per unit mass or differential form. Okay. So these are just the standard forms of the equations. And like the last point here, right? Delta E is equal to zero if it's a cycle. Okay. So no, in terms of, at the end, you don't have any change in internal energy. This is it, Q equals W, right? So here's some of the equations. We can think about it. And like, here's where the for a stationary system comes from, right? We say, heat minus work, essentially. It's going to be just the change in internal energy plus, whatever kinetic energy or change in kinetic energy you had and whatever change in potential energy you had. So for stationary, these two just go to zero. Okay. So the end result is like, over heat coming in minus the work out or boundary work and any other work that could be attributed to it. So this is like our sort of general form. And then here's the changes in internal energy. Okay. Okay. And, you can write it. Here's another way to write it, for constant pressure. You can write it in this form. And then you can rearrange the equation, right? And then you'll see what ends up happening here is that this becomes our enthalpy equation, okay? And then this is for constant pressure expansion or compression process, right? So once we have this constant pressure, we can write an equation like this. So it's just saying essentially, this is the change in, the difference between the heat minus whatever other work that's being done, and then the internal energy is just this one, two 2 minus 1, and then this is just the pressure or the pressure differences. Okay, if you were to write it in this form, right? Okay, and this is just essentially there's our boundary work, right, for constant pressure. Okay, and then you could also write it in this form, right? So you write it as just the difference in the H2 minus H1, right? So if we continue on just from that, we're basically saying, the difference between the work in minus the heat out is that delta H. And then here's like your delta H. And then you bring the boundary work over to the other side, and this is where you're getting your equation for change in enthalpy equal to change in internal energy plus the boundary work. Okay, which you'll find that to be useful. So continuing on with that, if it's constant pressure, right? Pressure is constant. We can rewrite the equation like this, and of course you see that these two essentially are, the boundary work plus change in internal energy is just equal to delta H. Okay, so here's the equation for constant pressure. Okay. Well, in a case like this, so if it's against the volume, there's no work and no energy transfer, right? Because you have no change in pressure, so you have no work being done. Okay. And here's the equation for expansion of water, right? So how we can rewrite that, or how we can implement our equation for change in internal energy. And in this case, it's just saying like it's unrestrained, right? So you could just write that change in. This is just in terms of, so you're not doing any work. So you just have the equation as being Qn equals change in internal energy. And then rewriting it in terms of so this case, so it's unrestrained. Then you write in terms of the specific internal energy. So it's a different way essentially than writing this, right? So you have a change in those specific internal energies times the mass. Okay, the same thing. It's closed system, right? So those are sort of the quick overview of the main points. Now it's a matter of going through and looking at some examples of these to see them in action, or the principles in action.